So last week we talked about faults and solar panels. Cool. So just going over those solar panels. What are the main components of a solar power system? Yeah. Panel inverter. Sun, yeah. MPPT controller, yeah. DC breaker, AC breaker, yeah. Yeah. Oh, good, Blake. Yeah, you guys got all of them plus a few extras. Yeah, so you got the solar panels or photovoltaic modules, which convert sunlight into direct current DC. You've got the inverter, which converts the DC electricity into alternating current AC for use in homes and businesses. Your charge controller for battery-based systems, so it regulates the voltage and current to prevent battery overcharging. Your battery storage, if it's applicable, stores excess energy for when sunlight is unavailable. Mounting system, so it holds solar panels in place either on rooftops or ground mounted structures, and wiring connectors ensures safe transmission of electricity between components. And just a little other tidbit about solar. Um, until recently, one of the issues with solar is that the inverters basically used a AC signal from the grid, especially in big solar arrays, to basically copy the AC waveform of the existing grid, and that's how they created their sine wave. Um, but a few years ago, basically there was a lightning strike in Texas that took out a lightning arrestor, and because the AC signal dropped out, the inverters didn't know what to copy, so they just shut down and stopped transmitting to the grid. So that is one danger with some of the older solar systems. If they don't have an AC waveform to copy, they can't spit it back out. But technology has improved a lot since then. Cool. What tests should be conducted after installing a solar power system? Yeah, voltage, insulation, polarity. After a solar install, what test should you do, Ryan? So you've just installed a solar power system. What test do you need to do? Okay, so after you install a solar power system, you need to do a continuity tests, so check for proper wiring connections and no open circuits. Insulation resistance test to ensure all cables are not leaking current to ground. Voltage and current measurements, so confirm expected output from the solar panels. Perform ratio testing, so it compares the actual power output with the expected values. And thermal imaging if you can, so identifies overheating components. And then obviously your standard polarity checks, your correct circuit connections, checking that your bonding to the solar panels is good. Earth loop, I suppose it's more earth continuity. So what are some advantages and disadvantages of using battery storage in a solar power system? Yep, power storage. Yep. Cost and complexity. Yeah. Batteries have a limited life. Yep. Yeah. So some of the main advantages to having a battery um, storage for a solar system. So it provides backup power during outages, stores the excess energy for nighttime or cloudy days. It reduces the reliance on reliability on off. So it reduces the reliability on grid electricity and enables off-grid independence, especially if you don't actually have access to the grid. It's good. Yep. So the disadvantage is high initial cost. Costs a lot for battery installs these days. Well, it's come down from what it used to, but it was a very high initial cost back a few years or even a year ago. The batteries do degrade over time, so they have a shelf life. Um, so they'll only last for a certain period before you need to replace them. Um, it requires maintenance and proper ventilation, so you can't just stick batteries wherever you want. You do need to maintain them and give proper ventilation. Um, and so low energy efficiency due to charge discharge losses. So there are losses when you're charging and discharging. Cool. So what safety considerations do you need to take with when working on solar power systems? What things do you need to keep in mind when you're uh, working on solar systems? Explain, Timothy. Yeah, yeah. So you need to cover the panels because they will continue to charge. Yep. Problem is, even if there's no load, they still generate voltage, so there's still a potential difference. No current flows, but the voltage is still there. Yeah. One thing to take into consideration is that because there's that continuous voltage, when you go to pick up the panels, and if you have your one hand on the panels and you touch the rail, which is earthed or bonded, there is a chance of that going through you, the DC voltage going through you. Obviously, they're heavy, they're awkward. If you're working on a windy day, they can just act like a sail and kind of pull you one way or the other, which is why you need to ensure you've got adequate roof guards when you're working on the roof. To be fair, I don't know a lot about solar, but yeah, I think the plastic connectors or the MC4 connectors would prevent that. But there's still a chance, like if the cable's damaged or if there's a short to the frame, it's potential of touch voltage. It's not like a piece of equipment that you can just disconnect and there's no chance of voltage. With a solar panel, if they're in direct sunlight, they can continue producing. Even in low light, a lot of the newer ones are that efficient. So troubleshooting common solar problem system issues. So what are some common issues you think you'd have with a solar system? Yeah, pollen buildup on the solar panels, low power output, animals, yeah, especially if you're dealing with bird strikes, dirty panels, yeah. Yeah. So when you're troubleshooting issues, solar system. So yeah, one of the things, yeah. So when you're diagnosing solar system issues, you've always got to check the voltage output, the DC voltage output. So you're going to need a proper decent multimeter, not just a standard like voltage tester. Um, yeah, and then obviously going to need to check the panels. I heard of one time where one of my ex-coworkers went to have a look at a job where they complained their solar output had dropped. What they hadn't mentioned is that they had a tree fall on the roof of the house and it cracked half the panel, so half of their output had dropped. I mean, luckily they were on microinverters, so it kept working. But yeah, if it's not a microinverter system, a basically one panel goes, half or a whole of an array can be taken out. Cool. So let's move on to test instruments. So test instruments for us are essential tools in the electrical industry to measure, diagnose, and troubleshoot electrical circuits and components. So the devices that help electricians ensure that electrical systems function correctly, comply with safety regulations, and operate efficiently. Without test instruments, identifying faults and ensuring safe installations will be challenging. So the uses of test instruments, so measuring electrical parameters, so we can use it to test for voltage, current, resistance, power, our IR tests or insulation resistance tests, earth resistance. You can use them to diagnose electrical faults, so they can help us identify short circuits, open circuits, faulty insulation, poor grounding, and incorrect wiring. And to ensure electrical safety, so verify circuit protection devices, check for dangerous leakage currents and prevent hazards, and compliance and maintenance. So ensure systems meet legal and industry standards and conducting. So what different test instruments have you used during your apprenticeship so far? And what did you use them for? Multimeter? Phase rotation, cool. Oh yeah, data cable tester. We're talking like one of the big fancy Fluke ones, or just kind of normal continuity 8 lights cable tester. Normal. Oh yeah. Mega for earth bonding, yeah. Oh yeah. Just the minimum voltage operated circuit breaker. Hey, multimeter and a mega, yep. So we can categorize test instruments based on their function, such as, okay, what do those acronyms mean? CMC, CPC, VLF. I'm intrigued now. What do they mean? Omicron test gear. Okay. Yeah, the types of instruments, so we can categorize them based on function. So voltage and current measuring instruments. So they measure electrical potential difference and current flow. Resistance and continuity testers. So they check for circuit integrity and resistance. Power and energy meters assess energy consumption and power quality. Your insulation and earth testing instruments. So they evaluate insulation resistance and earthing effectiveness. And specialized electrical testers. So these detect faults, harmonics, and specific electrical conditions. They're not something you'd use every day. So, right, time for cool. So 1 moment. Cool. Can everyone see the PowerPoint, the test instruments unit standard? 32641 Cool. Right. Cool. So going to look through this. So section 1, we're going to look at some test meters, multimeters, digital and analog. Then we'll look at some clamp meters, IR testers, continuity meters, voltage testers, thermal imaging cameras, RCD testers, and then we'll take a look at the earth fault loop impedance testers and IEC category ratings. So introduction to test meters. So this is your basic digital multimeter. So it's a type of multimeter that uses a digital display to represent the measured quantity in the form of digits. So there you've got a Fluke 83, which is one of your more standard multimeters. It's still a good basic meter. The characteristics of a digital multimeter, so they're more accurate readings than an analog multimeter. The chance of misreading measurements values is reduced because the screen displays exact numbers. They may have an auto polarity function, and digital multimeters are more robust without moving parts like the needle of an analog reader. So digital output can increase the range of applications that are run by computers. Measurements on the screen of a digital reader can be locked or stored. The input impedance of digital multimeters is high and it is constant for all the ranges. And digital options usually come with an auto range feature. So yeah, it just reduces the risk having a digital one versus analog. Analog ones were very open to misreading depending on what angle you were looking at the meter. If you were at a slight angle, you could get a funny reading. Cool, and this is a example of an analog meter. So a type of multimeter that uses a needle on a scale to measure electrical quantities like voltage, current, and resistance is known as an analog multimeter. The reading on the scale reflects the quantity to be measured. Its basic principle of operation is such that the pointer shows deflection according to the force on it via a coil and a magnetic field in the permanent magnet, and that permanent magnet may become demagnetized over time, decreasing accuracy. So they're ideal for reading fluctuating signals where a range is required. They do not have as many advanced features as digital tools. They're easy to accidentally misread. The wrong scale can easily be selected by the user, so you could accidentally damage the meter by putting it onto 10 amps when you're reading 100 amps, and then the needle just goes whoop all the way to the wrong side. They're often not as accurate as digital tools. They can be easily damaged when the polarity is reversed. Better suited for electronic engineering, and they're less susceptible to electric noise during measurements. So they do have their advantages, but generally for just general electrical or electrician work, not ideal. Cool. So these are the different multimeter settings that you can get depending on your multimeter. So here you've got your diode check, so checking diodes and electronic components, checking which way they go. Continuity check, bell. So this is one you'd use when you're belling out faults. So you hook one end on a cable, you're not sure where it goes into a junction box at the other end, and then you can quickly tap the cables together and it'll make it beep. So your resistance setting, so that's your ohms, so it'll give you an accurate resistance reading. Your DC voltage setting, so you have to select DC voltage when you're wanting to check DC voltage. Some multimeters, like I think the Fluke T5 and T6s, will automatically switch between AC and DC. And you got your AC voltage setting there on this particular model. So this is the voltage or so continuity. The continuity check or the bell, it does show resistance on the screen, but it's more to check that there is a continuity between the two. Whereas when you're checking for resistance, you're wanting to know what the resistance value is. So you can use like a Fluke T5 and T6, the continuity and the resistance setting is the same thing. The bell is just automatically on. But sometimes you want to check the resistance and continuity without having the bell annoying you. So that's your voltage resistance socket for your red probe. You've got your direct current settings, so your microamps, milliamps, or 2 amps. And you got your alternating current settings for microamps, milliamps, or 2 amps. And then you got a current socket there for the red probe. So that's if you're wanting to check current. So you would have it in series with whatever you're testing. And then the common or ground socket, which is your black probe. Cool, so voltmeters. So a voltmeter is an instrument used for measuring electrical potential difference between 2 points in an electric circuit. So a parallel connection is used because a voltmeter is constructed in such a way that it has a very high value of resistance. A parallel connection also ensures that the volt drop across all the components, meter and load, are almost the same. An ideal voltmeter should have an infinite resistance during zero current with no power loss in the instrument, but it's not ideal. Many of them aren't infinite resistance, just very, 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 very high resistance. And then you've got ammeters. So an ammeter is a measuring device used to measure the electric current in a circuit and connected in series with a device to measure the flow of current. Current is the measure of the rate of electron flow in a circuit. It is measured in the unit of the ampere, simply amp. Some digital meters have a separate jack to insert the red test plug when measuring current. So a lot of them will have one for current, one common, and then you'll have another one for your voltage and your resistance. Cool. So any questions so far about anything we've covered? So a voltmeter doesn't have to be a specific voltmeter. So your multimeter can read voltage, but you can get tools that all they do is measure voltage. Usually they come with as two probes, and it has lights indicating the magnitude of the voltage, but not a specific number. Cool. So now we'll take a look into section 2. So your clamp meters, AC. So clamp meters are electrical testers with wide jaws that clamp around an electrical conductor. Inputs for accepting test leads. Clamp meters rely on the principle of a current transformer inside the clamp meter, which senses the magnetic fluctuation and converts the value to an AC current reading. This type of measurement is convenient for measuring very high AC currents. So it's not good for measuring, normal clamp meters are not good for measuring low current. So you got the basics of the circuit there. So you got the wire going through the coil with a number of turns on it. So current to voltage conversion circuit, a rectifying circuit, analog to digital conversion circuit, and then a display circuit. So I, current under test, primary current, N number of turns on CT winding, I secondary current on CT. So there's a lot that goes into it when you cut open. So that is one of the Fluke models, I believe. So yeah, it's basically a coil. It basically turns it into a sort of transformer where the clamp wraps around the cable and the cable induces a current into the windings through magnetic flux. Obviously, it's not just clamp type. You can get the Fluke T5 and T6 series have the U opening at the top, and if you stick a cable in that, it'll read current as well. Again, they're good for measuring high AC currents, but they're not usually always very accurate. Some of the Klein ones can be, but if you're measuring very low currents, you need a specialized type. And then you've got DC. So direct current flows through conductors in a fixed polarity. The magnetic field around the conductor does not change. So conventional clamp meters will register no reading. DC clamp meters work on the principle of the Hall effect. So you've got the Hall element, transformer jaws, there's a gap. So magnetic flux is this gap. Yeah, it's a lot more complicated, so much more specialized. So they're usually a little bit more expensive. Cool. So your insulation resistance testers. So how many of you guys have used your insulation resistance testers so far? And how many of you have had your boss zap you with the insulation resistance tester? I've been through, yeah, yeah. We had so we have classes here called pre-trade. Basically, guys come here for 3 days a week and do training. It's essentially the first 2 years of your apprenticeship, theory-wise, and a little bit of practical. And so we had a new bunch start this January. And we gave them the mega installation testers to practice testing their leads, and about 6 of them managed to zap themselves. We're pretty sure 2 of them did it on purpose. No idea why. Yeah, so insulation resistant testers are used to test the integrity of the insulation of each conductor to ensure that no leakage current exists. That leads to incidents which may be serious in terms for both safety, people and property, and the costs of production stoppages. Obviously, it's essential to identify this deterioration quickly so that corrective steps can be taken, and regular insulation testing on installations and equipment helps to avoid such incidents through preventative maintenance, detecting aging and premature deterioration of the insulation properties before they reach critical levels. Sometimes you don't need an insulation resistance tester to identify that wiring is gone bad. I've had a couple of jobs when I was doing resi maintenance, where I had to just use my multimeter across the mains or across the circuit, phase to neutral, and I was getting straight continuity dead shorts in several locations. And there were no appliances plugged in. Everything was switched off. All of the light bulbs had been taken out. There was nothing that could have been causing the short apart from damage to the cables. Yeah, so those properties got rewired. So your insulation resistance is measured using a portable IR tester. So the principle is essentially an ohm meter with a built-in generator that's used to produce a high DC voltage, usually measures at least 500 volts and causes a current to flow around the surface of the insulation and will give a resistance value usually in mega ohms. And one great way to find a fault, if you're getting a fault on a circuit, switch it to 1000 volts DC and hook it up and leave it running. Either the fault will clear itself or it will pop and you'll be able to find the fault. It's not always a good idea, but it works in a pinch. So for testing 400 volt three phase or 230 volt single phase installations, AS-NZS 3000 requires a 500 volt DC test voltage as a minimum. The minimum acceptable reading is 1 mega ohm or 1 million ohms for any installation, appliance, or motor. Exceptions where the insulation resistance can be lower. Special considerations are required when testing circuits in which sensitive components are used. Does anyone know how to test a lighting circuit if it's already got LED lights installed? Yep, you can do a 250 volt test. Yep. Okay, the main important thing is that you are testing your phase to earth or your phase to earth. So what you can do is you can take the phase and neutral at the switchboard, twist them together and test between the phase neutral and the earth. Because the LED lights use a transformer before the driver, basically you're forcing the transformer to not conduct because you're passing current down both sides of the transformer windings. So that way current can't flow through actually into the LED circuitry itself. So that way you can perform a 500 volt test on the wiring if you connect the phase and neutral together and then test to earth. Cool. So this is an example of an ohm meter or a continuity tester. This one can do voltage, but as you can see, it can only measure certain voltage ranges. It can only tell you that it's 50 volts or a bit more, 120 volts or a bit more, 230, 400, and maybe fluctuate between the two lights to say it's between these voltages, but they're usually not that complex. So it checks for breaks and conductors and connections. So you connect leads to both ends of the circuit. If the circuit is continuous, tester beeps or lights up. Common applications. Common applications is just like fault finding, or if you're doing, you're checking motor windings that they're actually connected. Or you're checking your earth connection by checking the earth to neutral with an MEN link installed. Cool. So voltage tester, non-contact. So it detects live voltage present without physical contact. It's useful for quick safety checks. So how to use it? You bring it close to a live wire, observe LED or sound indicator. Precautions to avoid false readings. Don't use it. I personally don't think they should be used because you guys should be using a proper multimeter to double check that you have isolated your circuit correctly or if the circuit is live. Yep, it's a good general indication, but just remember, even if it says there's no voltage, there could be voltage. Even if it says there's voltage, there might not be voltage. It could also be reading the DC voltage. Cool, so thermal testers. So thermal testers measure the infrared light emitted by all the objects in view. The light scanned by the detected elements create a pattern called a thermograph. The impulses are sent to a signal processing unit, a circuit board with a dedicated chip that translates the information to the display. The signal processing unit sends information to the display where it appears as various colors depending on the intensity of the infrared emission. Do any of you guys do thermal checks on anything? I'm guessing a few of you guys in the HV world do. Ah, drones with thermal cameras or just drones? Oh, nice. Yeah, I think that'd be a great job for when I get older if I don't manage to pass my inspectors is go and just use a thermal camera to test boards in factories and commercial properties for insurance purposes. So common applications, so monitoring and fault diagnosis of electrical equipment. Equipment can be surveyed for faults while in operation. It'll show if there's loose connections and terminations. Overheating, yeah, overheating capacitors, couplers, cables, windings, bearings, buzz bars, and insulation materials. Aging components can be detected because old components will give off quite a bit of heat. Cool. RCD testers. So, in an ideal installation without earth faults, an RCD would rarely operate. Several years may pass before the RCD has to operate, and in the duration, the RCD may freeze and not trip when required. So, regular testing is essential. The test button trips the device during a current imbalance. However, this method is unreliable for verifying RCD functionality on leakage faults, as it trips even without a protective earthing conductor. An RCD test instrument triggers a trip, both AC and pulsating DC faults. Yeah, the working principle of the RCD there. So you got a sensing coil there and a relay. So current flows through the live and neutral conductors, and because of the way the toroidal coil works, or that round ring of metal you see there, so basically that's a transformer. So as long as the coils on both sides are equal, it doesn't the magnetic flux through both are equal. But as soon as there's a load imbalance, it triggers a current inside the third coil there, which leads to the relay. And that gets translated into a quick magnetic repulsion and pushes the the contacts apart. And that's the basic operation of an RCD. And so what happens with the test button is it bridges across the neutrals or line side, thus creating, usually should be the neutral side, and thus creating a imbalance. Yeah, it goes from neutral to line and basically causes a imbalance in the current, thus causing a fault, tripping the RCD. But it has nothing to do with the earth, so it's not a good way of testing if the RCD actually works. But how often do you reckon you need to push the test button? In a residential setting, how often do you need to test the RCD? When you're about to skid, uh, Now, domestic installation, you need to push the RCD test button every 6 months. So every 6 months, you need to at least push test the RCD button. One good thing to test though would be every 6 months do a RCD test, but obviously no one's going to do that. And not everyone who lives in a domestic property knows about this rule. Basically, every time you check your smoke alarms, you check your smoke alarm every 6 months, test your RCDs every 6 months, which is a bit laborious if you have RCBOs, which is my preferred install. I hardly ever install RCDs anymore. Cool. So these are some RCD testers. So you've got a Mitrel down the bottom left, a Fluke in the middle, I can't remember the name of that. I remember it's an English brand, and those are usually pretty good. And then you've got your kind of plug tester, push button one in the middle on the right, and then at the top you've got a slightly better plug-in one. Cool. So they permit selected leakage current values flow to earth. They detect how long it takes the RCD to operate under these simulated fault conditions. So RCD testers require that the person carrying out the test is competent using the test instrument. The electricity supply is connected to the RCD protected sub-circuit under test. Personal protection. The RCD has a maximum rated residual operating current of 30 milliamps. Operates within a maximum time of 30 milliseconds. Cool. So when you push an auto test on an RCD tester, how many times does it test the circuit? Okay, so when you use an auto test function on an RCD, it will test it either 6 or 8 times. So you have to push the auto test and then go reset the RCD every time. So what it does is it tests it at half its rated current, at its rated current, and some will do twice the rated current, and then all will do 5 times the rated current. So it either does 6 or 8 times. And the reason it does it 8 times is because it tests it at 0 degrees on the sine wave and at 180 degrees of the sine wave. So it tests at both sides of the sine wave to ensure that if the fault happens at one side of the sine wave or the other, the RCD will still operate. And then the optional extra test is to do a ramp test, because an RCD, even though it's rated at 30 milliamps, it may not trip at 30 milliamps. So you could do a ramp, because if you do the 5 times and it trips in a certain time, cool. But if you do a ramp test and it turns out that 30 milliamp RCD trips at 32, is it compliant? 32 milliamps. So if it's a 30 milliamp and it's tripping at 32 milliamps, what do you think is the lowest value it should trip at? So um, if you were to test the RCD and it's below 30, how low before you start thinking maybe you should swap it out? Because an RCD can be too sensitive as well. So there is somewhere in the regs, and actually, I will quickly. So me personally, as you're getting towards like 20 or below, um, yeah. RCDs have a sensitivity range and may trip at residual currents as low as 50 to 70% of the rated value, meaning a 30 milliamp RCD could trip at currents as low as 15 to 21 milliamps in some cases. But if you're getting, if it's tripping at 15 milliamps, to me, that's going to cause nuisance tripping, especially if you've got microwaves or things like that on the circuit. Um, yeah, so I would be tending towards like 22 up to 30 is okay. But anything below 22, I would be recommending to the client that your RCD is a bit too sensitive. Maybe we should look at replacing it just so you get less nuisance tripping. Cool. Cool. So earth fault loop impedance tests and IEC ratings. Cool. So earth fault loop testing, often simply called loop testing, verifies that if a circuit fault occurs in an electrical installation, sufficient current will flow to operate the fuse or circuit breaker protecting the faulty circuit within a predetermined time to prevent overheating and possibly a fire. So two loop impedance values are usually recorded. ZE, the external fault loop impedance, or ZS, the total system fault loop impedance. So fault loop impedance, so your substation transformer, so your ZE is from your substation transformer to your distribution board, and then ZS is from your substation transformer all the way to your socket outlet. So your ZE is done at the distribution boards, and your ZS is done at your socket outlet. So ZE is the external fault loop impedance, so distribution board to substation transformer. R1 is the phase conductor resistance, R2 is the earth conductor resistance, and ZS is the total system fault loop impedance. So ZS equals ZE plus R1 plus R2. Just remember, when we're talking about impedance, we're talking about the total opposition to current flow in an AC circuit, whereas total resistance is more for your point-to-point and DC circuits. Because with impedance, there are multiple current paths and parallel circuits, which, as we know from when we looked at resistance, resistance in parallel is a lower overall total resistance. But yeah, so when we're talking about AC circuits, it's impedance. When we're talking about DC circuits, it's resistance. Cool. So yeah, when you're doing your ZS, you do it at the between phase, neutral, and earth, and you at the switchboard, and then the other one should be plugged into the socket outlet. This looks like it's a UK style socket outlet, which it's also got blue neutral, which is annoying. But yeah, so when you're doing your ZS or your earth loop impedance, what it's doing is it's measuring the impedance path all the way from the earth pin that you're testing to the earth bar, through the MEN link, down the neutral to the center tap of the transformer or the neutral point of the transformer, back along the phase wire to the distribution board, through your circuit breaker, and then to your socket outlet. So that's the entire loop that it's testing. So it's checking that if there's a fault, the current will flow through the earth to the neutral, through the neutral, through the phase, all the way back to the circuit breaker and trip the breaker, and also not fuse it shut if your earth loop impedance is too low. The circuit protection, the current may be so high that the circuit protection fuses completely. Cool. Cool. So overvoltage rating. So the International Electrotechnical Commission, or IEC, has defined 4 voltage category ratings relating to an instrument's ability to withstand voltage spikes applied through a specified level of resistance. It defines its category rating. So you've got Cat 4, Cat 3, Cat 2. There's no Cat 1. So the resistance describes the source resistance of the testing apparatus, which limits the current using Ohm's law, I equals V over R. The maximum current of a 300 volt Cat 1 test is 1500 volts divided by 30 ohms, which equals 50 amps. So obviously your Cat 4 rating is a lot higher than your Cat 3 or your Cat 2. Most multimeters here in New Zealand are either Cat 3 or Cat 4. Cool. So understanding Cat rating. So your Cat 1 is for your electronic only. Cat 2 is for single phase and receptacle connected loads. Cat 3, 3-phase distribution, single phase commercial lighting. And your Cat 4, 3-phase at utility connections and outdoor conductors. You guys working in the distribution area, is there anything, do you guys have any that are higher? Like, do you guys have Cat 5 rated testers? Or are they a whole different category? Yeah, so do they have a category rating? So Cat 5 or just proximity? Okay, maybe go and check some of your testers tomorrow or ask some of your other guys if there's a category rating. I'd be interested to know. And that's the end of that. Cool. So just some quick recap questions. What is the primary function of a multimeter? Cool. So I'll give you guys some options. A, to measure resistance only. B, to measure voltage, current, and resistance. Or C, to test, actually, hold on. This might be easier. Oh, so yeah, first 2 questions. So yep. Wow, I love how they did that. Never mind, guys. Right. Most of the resources I get are given to me by people who work in Auckland who are not necessarily tutors and not necessarily working online. Cool. Some notes for you guys. Cool. So test instruments are essential for safety and efficiency in electrical work. Every electrician must understand how to use them correctly and interpret the results. Regular calibration of test instruments ensures accurate measurements. Some people believe that your multifunction testers or your fluke testers should be calibrated as often as we get requalified, so every 2 years. Um, Beware of the exposed probe tips of the IR tester. Shock hazards exist. 500 volt DC plus. And always check the test meter battery levels prior to commencing electrical testing. Nothing worse than starting a test and realizing your batteries are dead. I wonder. How this works. Right, so there are a couple of videos that were supplied with tonight. Cool, so that's the majority of the lesson. What I'm going to do now is I'm going to, just because YouTube is going to be annoying if I do it, I'm going to stop the recording